All right, this worksheet can be found on Canvas, so I'm just going to work through them one at a time and talk about how I decide which test to use and so forth. So the directions say state and prove convergence or divergence for each of the following infinite series. Be thorough and complete in your evidence. So we're actually proving that it's true. We're not just saying yes, it is or isn't convergent. Okay, so the first one, I just look at that and think, oh, that looks like a geometric series of sorts. We probably want to rewrite it like this, and running from 1 to infinity. Since there's one extra factor 2, I can pull that out, and then this will be 2/3 to the n. So just by rearranging a little bit, we can see clearly, I'm sorry, not to the n minus 1. We can see that that is a geometric series, and the ratio is less than 1, so we'd say geometric series with r less than 1, therefore it converges. Okay, so that was pretty easy. This one, definitely not a geometric or p-series, so if we run through all the different tests, there's nothing that I can really compare this to. I'm not sure. I mean, I could try to do the ratio test, but doing a ratio with natural log is not going to work out very nicely. So anyway, all this is leading to, oh, and the nth root test is not going to help, because taking the nth root of this is not going to make it any nicer. In fact, it'll make it uglier. So this looks like the possibility of doing looks like we might have to do the integral test. So to do the integral test, we got to, first of all, pick a function, and so we'll call my function to be f of x equals natural log of x plus 1 over x. That'd be my first step. And then we want to show that that function is, first of all, always positive, and natural log is always positive once it's bigger than 1. And notice that this is always going to be bigger than 1, isn't it? So in other words, natural log of 1 is 0. If you're taking the natural log of something bigger than 1, it will be bigger than 0. And so since the top is always bigger than the bottom, this thing will always be bigger than 1. So this is f of x is positive for all x greater than 1. And notice it has to be greater than 1. So, well, actually, I guess in 1 it's, no, even for 1 it works, because that'd be 2 plus 1, yeah, right. So then number 2, we need to show that it is decreasing. And so we could take the derivative. The derivative of this thing would be x over x plus 1 times the derivative of that, which the derivative of that would be derivative of the top times the derivative, let's say low d high, which would be x minus high d low, which would be x plus 1 all over x squared. So the derivative would be x minus x is 0, so that'd be negative 1. So that'd be negative x on top, and that would be x squared plus, or no, x cubed plus x squared on the bottom. And so since the bottom, when we're plugging in, again, we're plugging in positive numbers here, so the bottom will be positive and the top will be negative. So this is always less than 0. And then finally, and then we also have to need to show that this is continuous, and this is continuous everywhere but at x equals 0, but we're not letting x equal 0, so this is f of x is continuous for all x greater than or equal to 1. Oh, I guess we never said up here for number 2, we never said it's decreasing though. But you would say, have a line in here, since the derivative is always negative, that means f of x is decreasing. Okay, so then we met the three conditions. So now what we're going to do is take the integral. Okay, so we're going to do the integral, and of course it's going to be improper integral, so we take that by taking the limit as b approaches infinity of the integral running from 1 to b of the natural log of x plus 1 over x dx. And so then we need to integrate that. So the way you'd integrate this is using integration by parts, where you would let u equal the natural log of x plus 1 over x, and dv equal dx. And if you integrate that, you end up with the limit as b approaches infinity of x times the natural log of x plus 1, of x plus 1 over x, plus the natural log of x plus 1. And that's evaluated from 1 to b. Okay, so then we plug in our numbers. So that would be the limit as b approaches infinity of b times the natural log of b plus 1 over b plus the natural log of b plus 1 minus 1 times the natural log of 2 over 1, which would just be 2, plus, oh no, that'd be minus also, minus the natural log of 2. Right? So, of course, that's going to be a constant, so we don't have to worry about that. So the question is, what happens to this? So as b approaches infinity, this approaches 1, and the natural log of 1 is 0. So this whole thing is approaching 0, because 0 times anything is 0. And this one is just getting bigger and bigger without bound. This thing, natural log of a growing thing, is just getting bigger and bigger. So this is divergent, and therefore the series is divergent. Natural log of n plus 1 over n diverges. Okay, so here's another one. Looks like it's similar to a geometric series. This has a couple extra factors of 3, two more factors of 3 than it does of 4. So we could rewrite this as n running from 1 to infinity of 1/9 times 4/3 to the n. And when we write it like that, it's clearly a geometric series, so this would be geometric series with r greater than 1, therefore it diverges. Right? Part D, give myself a little bit more room here. Okay, so this one looks kind of like a power series, but it's not because of the plus 2n and the 2. So this looks like a good candidate for comparison tests. So we'll let a sub n equal 2 over, I guess I should say, I think we'll use direct comparison here. Direct comparison. and we're going to let a sub n equal 2 over n squared plus 2n. We'll let b sub n equal 2 over n squared, and then clearly a sub n, or I guess we should say n squared plus 2n is bigger than n squared. Therefore, a sub n is less than b sub n. So that meets the first condition of the direct comparison test. And we know that this series, n running from 1 to infinity, of 2 over n squared, is a p series multiplied by 2 with p greater than 1. Therefore it converges. Then my original series converges. 1 to infinity, 2 over n squared plus 2n also converges. Alright, there's D. Let's go up to E. Look at that one. That's definitely an alternating series. It's going to change back and forth from negative to positive. So we could use alternating series tests. So we're going to pick a sub n equal to 3 to the n over 2 to the 2n minus 1. That would be my a sub n, because that would be the same as that with so you can see that this is equal to negative 1 to the n times a sub n. Right? Okay. So we need to show that a sub n is decreasing and converges to 0. And that is going to be a problem. Because actually it's increasing, isn't it? Oh. So we're going to play around with this a little bit. This is going to be 3 to the n on top. I'm going to rewrite this as 2 to the 2n. Oops. 2 to the 2n times 2 to the negative 1. And that would be 3 to the n over, of course, that would be 4 to the n times 1/2. And that's going to be 2 times 3/4 to the n. So now we want to show that that thing is decreasing. It is, because of the geometric sequence with r less than 1. And we need to show that it converges to 0, so we'll take the, so anyway, a sub n is decreasing for all n greater than or equal to 1. And then also we need to show that it converges to 0, so they take the limit as n approaches infinity of 2 times 3/4 to the n. And as n gets bigger and bigger and bigger, we're taking 3/4 of 2 over and over again. And this is an exponential expression with the base less than 1, so that is going to approach 0. And so we met all the requirements. So therefore, this guy converges. Therefore, n equal 1 to infinity of negative 3 to the n over 2 to the n minus 1 converges. So we use the alternating series test there. I guess I didn't say that. The alternating series test. We'll say AST. Okay. All right. I've been waiting for this one. So here is a n factorial. Remember in the last video I wrote, I told you that if it involves factorial, you're probably going to have to use the ratio test. So here we go, ratio test. And remember, we're just taking the ratio of a sub n plus 1 over a sub n, and hoping that it's not 1. So we're taking the limit as n approaches infinity of n plus 1 factorial over 3 to the n plus 1. And remember, we're taking the absolute value of this, so that takes care of the negative. And then multiply that by a sub n flipped over because we're dividing by a sub n, so that would be 3 to the n over n factorial. Okay? Alright. So then, we're going to just simplify this. The limit as n approaches infinity of n plus 1 factorial divided by n factorial, that would just be n plus 1. And 3 to the n divided by 3 to the n plus 1, that leaves an extra factor 3 down here, so that would be over 3. So then the limit as n approaches infinity, as infinity gets bigger and bigger and bigger, of course the top's going to get bigger and bigger, so this is headed towards infinity. So is that equal to 1? No. Good deal. Is it, it is greater than 1, which means, so this is greater than 1, therefore our series diverges. Okay. Well, now here's a fun one. Okay, this is an interesting one. Looks pretty complicated, but if you think about this guy right here, the cosine of pi n, that means I'm only putting in multiples of pi into the cosine function. So if you plug in 1 for pi, that's cosine of 1. I'm sorry, cosine of pi is negative 1. If you plug in 2 for n, that's cosine of 2 pi, which would be 1. So really, this is just the same thing as negative 1 to the n. So it's going to behave like it's an alternating series function. So I think I would use the alternating series. So you could say, you could call my a sub n is equal to the square root of n over n plus 1, because that would be the same as this sequence if I multiply it by negative 1 to the n. So then we just need to show that it is decreasing and approaching 0, and then we got convergence. So first of all, if we let's see, can we show, let's try it this way. Can we show that a sub n plus 1 is less than a sub n? Let's see if that works. So that'd be n plus 1 square root over n plus 2. Is that going to be less than square root of n over n plus 1? So you can see that since we added less than 1 to the top and 1 to the bottom, this is true. In other words, the difference between the tops here is this is less than 1 bigger than that, and this is clearly 1 bigger than that. So this statement is true, which means it's decreasing. Decreasing for all n greater than or equal to 1. And then if we take the limit of square root of n over n plus 1 as n approaches infinity, that is approaching 0 because n is bigger than n square root of n, so it'll grow faster. So therefore, oh yeah, ultimately a series test, we should say that. Therefore, my original series n running from 1 to infinity of, of the square root of n times the cosine of pi n over n plus 1 converges. Okay, I think I'm going to stop there because this video is getting long. But I will finish these up off video and post the solutions. So let me know if you have any questions.